Okay, and I was going to talk. Did I say I was going to talk about the essay portion of the test or no?
No.
I didn't say that. Okay, let me take a look at something. Let's look at the test. So the test, the essay portion, right? Let's see how well you did on that. It wasn't bad. I think you could do more. Looking at your overall scores, I think you can do better. So for instance, when I look at this, I think I've already talked to you about this, right? We've already talked through the test last week. I'm thinking the other one.
We talked about the essay last time.
Yeah, because we spent a lot more time on how to do like the greenhouse effect, right? So that's what we did. Okay, so any questions about anything else? Is everything turned in that's supposed to be turned in? Some of you have not turned. Did you finish your geography lab?
Yes.
All of you guys have? Let's see where your geography lab is. I have Aaron, Shannon, Lena, Isaac, Julia, Ryan, and Zach. So where is the rest of your stuff? Also, you were supposed to turn in your Unit 1 classroom notes, and I've gotten it from 2 people. So, you're supposed to be doing your notes from class. Did you turn that in? No. Did you turn it in, Lena? Yes.
Yeah, I'm pretty sure I did.
So is it the rest of you who didn't realize it was due or something?
Yeah, I didn't see it I just scrolled down all the way to the bottom of assignments and I found it down.
Okay.
I can compile that and get that turned in.
Yeah, it just said on the instructions for the test, make sure you turn them in before the test. So I didn't put a due date on it. I probably could have, but just go ahead and turn that in later today then, okay, guys? Everybody good like that? Did you get through what chapter was on the precipitation processes?
I think that was 7.
Did you do that?
Yeah.
Aaron, chapter 7?
We read it yesterday.
Okay. How about you, Zach, Isaac, Ryan, Sam?
It was a bit of a busy weekend for me, so I began reading it, but I didn't quite get to the homework for chapter 7.
Isaac?
I haven't done it yet.
I think it was due next week, chapter 7. I think it was chapter 5 today.
No. I know, but I was asking you if you could do that. That would be good. So a couple of you did remember doing that. You didn't do it then, I take it.
No.
Okay. So there is going to be a lecture that I'm going to have you watch. It's going to go over one of the modules, but we're not doing the module, but it will help you understand the stuff that we're talking about today. Okay, so the first thing we're going to do is share the screen. I'm going to put this in here. And we put stuff over there. And we go to this. So the first thing we're going to talk about is how do we get a cloud? Now remember, a cloud is when a bunch of water vapor, what's the #1 fact about water vapor?
It is invisible.
It's invisible. When all of that vapor comes together and forms a droplet. Okay? When that's the case, this is called nucleation. Vapor turning into liquid. Now, do you agree that vapor it can be anywhere, right? It's flying around chaotically, randomly, all over. But it all has to come together to form a droplet. Okay, this is what's called a cloud droplet. So nucleation is vapor turning into liquid in the cloud itself. Okay, now the thing that we're going to talk about is this word entropy. How many of you know what entropy is? Zach, do you know what entropy is?
No.
Anybody? Tim? Entropy is a measure of randomness. Okay, so which has more entropy, the vapor or the liquid?
The vapor.
The vapor, right? So the natural, and you should write this down, the natural state of the universe is toward increasing entropy. So in other words, your bedroom, if you let it go, is going to get more random over the years, right? You're not going to leave your bedroom there, not touch it for a month, come back in and everything's going to be clean and organized, right? Things are going to decay. So the natural state of things is toward increasing entropy. So if increasing entropy is natural, then what does decreasing the entropy? In other words, organizing. What does that require?
Work. Like,
right? That's the term, work. It requires work. And we've already kind of dealt with work before. So when we want to decrease entropy, we have to do work. So do you agree that the natural state of the universe is for the water droplet to evaporate and go to the atmosphere? So if we wanted to go backwards, we have to decrease entropy because the droplet is more ordered than the vapor. Now, when we talk about saturation, what is the official definition of saturation? How would you, like in your own words, Ryan, how would you say what saturation is?
I would say the amount of water vapor is equal to the maximum amount of water vapor that can be made.
Okay, that is not untrue, right? You're right, but that's not what saturation is. Do you remember? It was something else when we first talked about it.
It's when a cloud forms.
No. What was the first time we talked about saturation in class?
Put your hand down.
Aaron, what do you got there?
She's trying to write something. One
Okay.
more. W A water vapor becomes a
I'm looking for two words, and if you're starting with water, what has she got so far?
when water vapor becomes T H S same as liquid. When the water vapor becomes the same as the liquid, she wrote.
Okay, so you're on the right track. I thought at first you said, Aaron, I thought you said when water vapor becomes tea, and I thought, well, that's a good idea. So what's the two words that I need to put in there? Because she talked about water vapor and water. Isaac? What's DE?
Is it something with the dew point?
Nope. Remember we talked about this? Lena, what is this?
Is it condensation and evaporation?
In what?
And the environment are the
In
same.
what? What is this?
Um,
You know this. Everybody knows this. DE. That's abbreviation. We use this word with ozone.
It's something
Oh.
equilibrium.
dynamic equilibrium.
Right? Saturation is dynamic equilibrium between vapor turning into liquid, condensation, and liquid turning into vapor. But in this case, in the first case that we dealt with it, it had a box. Remember, we had the box full of water? So in other words, the dynamic equilibrium is when we've got the liquid water and the vapor at the same time. When I'm in the air, when I start a parcel and I lift it, right? I'm lifting it up. There's no liquid water in here. So what's the dynamic equilibrium? The point is, does it matter where this vapor molecule goes? When it hits the water, it will become part of the water there. And if a molecule comes over here, it'll become a vapor molecule, I mean, a liquid water molecule there. But when I'm in the air, do you understand all of them need to come together at the same place? It's almost as if I said to you guys, let's go meet at Woodfield. And we went to Woodfield. What are the chances we're going to meet?
Pretty low because we don't have like a time.
Well, we don't have a time, we don't have a place, right? We're just kind of randomly going there and walking around, and maybe I'll meet one of you, but that's not a class. So if I said, well, what if I said a class would be considered 10 people? Well, what I need would be to have a lot more students walking around randomly, and then there's chances of getting to 10 people would be much higher, wouldn't it? I mean, there'd be a lot of people not there, but I would. So when we get nucleation, we can get what we call homogeneous nucleation. But in order to do that, we need the relative humidity to be like, let's say, for the sake of it, let's just say greater than 120%. In other words, we need more vapor than we're supposed to have. And the reason for that is we don't have liquid water for the vapor to condense onto. So we need 120% relative humidities, which means we're at greater than 20% what we call supersaturation. And that's homogeneous nucleation. Now, homo means what?
Same.
The same. Genius is same kind. So in other words, this is pure water vapor condensing into a droplet. This is not easy to get to. We say we lift the box until the relative humidity reaches saturation. So what we end up wanting to have then is we will add a thing. What's that stand for?
A cloud condensing nuclei.
Right? Cloud condensation nuclei, nucleus, a single one, right? So we're basically saying, hey, give the vapor something to be attracted to. We might consider that hydrophilic, or hydrophobic is opposite, fear of, repelling. So water vapor comes to it. And when we have this CCN, some other particulate, we now have heterogeneous nucleation. And there we only need relative humidity of around 100.7%, let's say, which is still 0.7% supersaturated, but it's a lot easier. In other words, we would be much more likely to get a class if I told you to meet at a fountain. Then you kind of go to the fountain and you're like, oh, there's everybody, right? So because I've got CCN, something different than just vapor, I can get this. Now, this is all happening at the microscopic level, right? This is happening at the very small level of molecules condensing into liquid water. So what I want you to understand, though, is that when I'm lifting a parcel, we aren't worried about this. We are saying the air saturates at 100%. But in reality, it saturates before that. Actually, I think I told you a little bit. Remember when we talked about this haze? We get condensation at around 80% relative humidity. But as soon as we get the water droplet, what happens when the relative humidity is only 80%? I found this on the web. Oh, shut up, Siri. What happens when the relative humidity is only 80% and molecules get together and form a droplet? What will that droplet do? Are you guys there today? You're awfully quiet. Hi, Tim. Tim's just a set of eyes today.
Gee.
It's been sending me in and out of the lecture. I don't know what's going on.
Yeah, that's okay. I mean,
I
it's not.
Internet and all that garbage.
What do you say to my question?
Wouldn't the when it evaporate?
Yeah, so you get a bunch of molecules that get together and they go, oh, I'm a droplet. But then the relative humidity is less than 20%. What is that droplet going to want to do? Evaporate. So how long do droplets survive in the air? Not very long, maybe a couple of seconds and then it goes away again. But when I look at a cloud, do you understand that there's permanency to it? The droplet is there for a while because it's 100% relative humidity. It doesn't want to evaporate. It's like once it's in the droplet, it's like happy. It's like, I don't want to turn to vapor. There's no room for me there. Okay. So this is what's happening in the cloud. Now, this stuff, this relative humidity, this supersaturation is actually going to become much more important when we start looking at something else that happens. But this is how we get a cloud. Okay. 120% we're not going to get. 100.7% easy to get to. So if you ever look at a cloud, have you ever seen the little clouds? Like I saw this the other day. You see the cloud forming and then kind of near it, there's like some whiteness. It's not like perfectly the cloud. Sometimes you have really crisp cloud and you have sort of cloud and then there's sort of a little bit of grayish blue stuff and then it's a little bit clearer away from it. So look for that in the future, okay? So now we've got cloud droplets. This droplet is super small, right? In order for it to be a raindrop, it's about 1,000,000 times bigger, more massive, whatever. Okay? So it's 1,000,000 times bigger. So how does this small droplet become 1,000,000 times bigger? That's what we need to talk about. How does this cloud droplet, and usually, by the way, that word droplet is really small, become a raindrop big enough to do what? Right? Question mark. So how does that happen? Tell me. Man, poor Tim. Poor Tim keeps dropping away. What do you say, guys?
Would it have something to do with like pressure and like pushing them together?
Welcome back, Tim. What do you mean?
I don't know. That's just like one of the ways I kind of thought of
Here,
is that
go here, guys. Go to class notes. And this is all in your class notes. Right? So what we need you to do is because you didn't do you didn't really do what I had asked you to do, was to try to get through this stuff. I'm going to do this for a second. I'm going to stop sharing and I'm going to record.
I would say that, because it says in the textbook that they like both mean to, I'm sorry, my dog's barking, both mean to merge into bigger droplets. So is there a difference between the two, or are they the same thing?
Well, what do you think collision and coalescence means? How about the rest of you guys? What does a web search bring up?
coalescence is to come together to form one mass or whole.
Have you seen this before in your life, Zach?
Well, looking at the picture that's on the page, it does remind me of like when you're in the car and it's like raining, you have the water droplets and it's rushing down, it's all coming
Okay,
together.
now let's talk about that. You're in the car, you're watching raindrops on the window. Collision means they're going to hit. Coalescence means they join together and make a bigger drop. But what do you know about that process that you should have experienced in your life, because you're a human being who drives in cars, when you watch those raindrops do that? Describe your experience. You've had that, right, Ryan?
Yeah.
What do you know?
I don't know what else to add. They just combine together. Like two drops would combine together.
Do they all do that?
No.
Well, discuss what you've seen.
I guess if they're too big, they might not form together.
What do you think about that statement, guys? Everybody else?
That makes sense. I mean, yeah, if they're like too big, they don't like merge together. So that could be because of like the water tension, maybe. That kind of like.
How does it start out?
There's like little droplets at the top of the window and then runs down.
We're going to do a lab. What I want you to do is we're going to take 5 minutes for you to do this and report back what you do. Okay? So I want you to go, and do you have a piece of glass or a glass cutting board, or maybe some sort of plate that's fairly flat? Okay, so grab that, go put your hands in water and spray the water onto the plate. Okay, so that they're just drops. So you're not pouring the water, you're just going to spray some drops on it. And then turn it on its side and tell me what the drops do. And report what you see, but be detailed, be observant. So Kevin, you and Aaron, you get that? You could do this?
Yep.
Okay, so right now it's 1:28, be back at 1:33. When you're watching these things go down, the little ones sit there and don't hit each other. In fact, they may not even move. They're just kind of floating around. The bigger the drop, the more that it collects. The more that it collects, the faster it starts to come down. So they're getting larger and larger, it's almost like exponentially, right? And when you're watching the side of your window, you see them, and then you see that really big drop, and it kind of squiggles coming down, and it goes all the way down to the ground, just like, whoa, that's a big drop. And each time they hit, they coalesce. Now, here's the thing. Imagine that you're driving on a like a cornfield road in August. What's your car going to run into? And if you said a farmer, that's a bad thing. What's your car going to run into? What are you going to hit a lot of?
Bugs.
Bugs, right? You're going to hit a lot of bugs. Now, when you're doing that, do you understand there's this airfoil around your car? If you have a small bug, what will that small bug do? Probably goes around it. What kind of bugs are you going to hit really hard?
Big
Those
ones.
Yeah, you ever hit those little mustard bugs? I don't even know what they are, but it's like there's a big streak of yellow on your car. Those are really good. I don't know what they are, but it's like
Mustard bugs.
Well, it looks like somebody squirted mustard on your windshield because it's really bright yellow, like French's mustard. Or if you get the bloody ones, those are gross. You're like, oh my God, what the hell was that?
Ever hit a lightning bug?
Lightning bugs are awesome because when you hit a lightning bug, what happens? And I did this.
Does it have like an afterglow?
I feel bad. I used to hit lightning bugs with badminton rackets or wiffle bats. And when you
My
hit,
friends
we
used to like.
we used to have thousands and thousands. Now there's hardly any, but there used to be all over the place. We catch them. They're the only bug I like. But when you hit them with the bat, what happened?
Back close of it.
The light would stay on. It just goes. Psh,
Yeah. So when I was little, my friends, I didn't do this, but my friends would smear the lightning bugs on a floor.
Yeah. You get that nice.
I didn't like it.
So I don't do that anymore. I catch lightning bugs, but isn't that the way you catch a lightning bug, like this? With your hand curl? Why is it that I don't want to touch a bug except lightning bugs? They're like, I like the lightning bug crawling in my hand. I don't care. Every other bug, I'm like, gross. Lena, do you like bugs?
Yeah. Oh, sorry. The dogs, like praying mantises. Those are so cool. Like, yeah, love
Do you
bugs.
pick them up and play with them?
Yeah, I'll do it for spiders too if they don't like freak me out too much.
God.
I don't know why.
Is anybody else afraid of spiders or just me?
I don't like bugs.
Better not come near me.
Is there what are you afraid of? What creature are you afraid of?
Dude,
Tim?
centipedes are terrifying.
Tim, you must be afraid of some creature.
I'm thinking.
Ryan, what is yours?
Scorpions.
It's good. Yeah, nobody wants to.
Any specific?
Aaron, what are you afraid of?
Yeah, don't come near me then.
Any of you afraid of snakes?
Yeah.
Maybe like a millipede or something gross.
Oh, those are gross. And they're
The
fast.
Yeah.
The
I'm-
only
They
spiders,
break apart so quickly. You just take a flipper and they
the
shatter.
only spiders I'm afraid of are, that we have around here are recluses and black widows.
Yeah, those are brutal. Brown recluse. Aaron, what did you say you were afraid of? Kevin, what's you afraid of?
He says sharks.
Sharks. Well, do you have a lot of sharks bothering you? I'm afraid of elephants. So I have this protection system that I bought to keep elephants out of my yard. It must be working. Okay, so anyway, so the droplets, that's the way they work. The small droplets, when they hit each other, and if you looked, if you were to like blow them, they'd probably miss each other. They move around the airfoil. But the bigger the droplets, the more likely they're hit. So for collision and coalescence to be an efficient way to grow a raindrop, what has to be true? Write that down. For collision and coalescence to be an efficient way of growing a raindrop, the drops fill in the blank. What do you think? What's the answer?
Do they different sizes?
No, not to begin with. They have to be big though. So in order for collision and coalescence to be effective, the drops have to be big. But how did, and Lena, you kind of alluded to the book saying this, how did they all start? Really small and they're all the same size. So collision and coalescence does not initiate raindrop growth. It works eventually.
It,
But
it would just
doesn't
enhance
initiate.
it, right?
What'd you say, Sam?
It would just enhance it,
Yes.
right?
So here's the thing. There are, well, I'll define this in a second, but if I got only collision and coalescence, what kind of precipitation will I end up with? If it were only collision and coalescence, what kind of precipitation would I end up with? There's a name for it. What's the answer? Anybody? What's that stand for? What's that the symbol for? Hello, big fly. Drizzle, right? That's drizzle. So when you see drizzle, you can say, well, there's only collision and coalescence going on. So that's not a very effective way, right? When's the last time we had 2 inches of drizzle? Never. It doesn't accumulate. So how do we get bigger other than coalition and coalescence? And that's called the Bergeron process. The Bergeron process. Okay, now, hold on. Pause the share. That's not what I want. I hate adjusting the windows like this. So I'm going to pause you guys again for a second. I got to figure out how to do this better. Oh God, I'm sorry guys. This is just so stupid. If you knew what it's like to be on my side right now. Pause. So what do you have for what vapor pressure is? Now we did talk about this in class at some point, right?
Okay, so yeah, it's the pressure exerted by water vapor. So yeah, so this is like, so basically what we went over in the notes is that, what was the guy's name? But basically like that, like 2 gases added together would equal like the same pressure of those pressures combined, you know? So vapor pressure is
Zach, I'm not sure I understand what you meant.
yeah, I'm kind of like, like
No, it's okay. You're talking through it, right? Because right now this is right. We're trying to figure out ways to learn. I need you to learn better, and so you have to figure out how to discuss something. So you're reading stuff. You're like, well, I don't know what these words are. There was a long time ago. I remember I took a class in education, and there was an example of reading a paragraph. And the person said, look at this paragraph. Is there a word in there that you don't know? And the answer was like, no, I knew every word. But they put them together in such a way I didn't know what they were saying. And that's really what learning is about. How do I make sense out of things? So how do you make sense out of stuff that I've written here, like a textbook or my notes? What do you have to do to it? Don't you break it down into simple things that you can understand? So, Isaac, what do you know about vapor pressure?
Well, when I'm looking at the definition of it on the notes, and it says part of the total air pressure that is a result of vapor molecules.
Okay, so can you give me a for instance? Can you explain it in your own words based on that?
Let's see.
By the way, what's the symbol?
Symbol E.
E, like little e, right?
So isn't that determining the amount of vapor molecules that are above liquid? And then
Okay,
I think what I'm thinking of is capacity.
here, let me ask you this. I have a box of air. What do you know about the box? What temperature is the box of air? Oh, I better do this. This is on the test. What temperature is the box of air?
You know,
Ryan?
What temperature is the box of air? I don't know.
Okay, everybody, let me see you. Grab a box of air. What's the temperature of that air?
Some temperature.
Some temperature what?
Um,
We did this first unit test. What temperature is it? Aaron?
same as the outside air.
Well, it is, but what temperature is that?
just
It's some temperature. What temperature is it, Lena? Think abstractly.
Yeah, I'm pulling a blank.
Here,
W.
Kevin, what did Aaron say?
She's still working.
So here, can I give you the answer?
Wait.
It's some temperature T.
Oh yeah.
What's the volume of the gas? How big is this?
some volume V,
Some volume V. How much mass is in it?
some mass M,
Some mass M. What's the pressure?
some pressure P,
Some pressure P. Now we were a little bit more specific. What pressure did we say it was?
um,
More than just P.
the
It's the pressure inside, right? Remember this?
Yeah.
What's the pressure outside?
same as the pressure inside.
Right, okay, so it's the pressure outside, right? So guys, listen, the pressure inside, what's the pressure inside? PI. What's the pressure outside? PO. Now, Zach, what's the relationship between those two?
The same.
They're same.
Pressure outside.
But do you agree that there's pressure? And I've said this how many thousands of times? What's our working definition of air pressure?
The weight of the air above us.
Okay, so if I have air that's above me, what makes up the air? What's the air made out of?
Molecules.
What kind?
Would just be like some gas.
Well, you know what it is. What gas is most of the air?
Water vapor?
Is it
What?
nitrogen? Wait,
Nitrogen. How much of the air is typically nitrogen?
78%.
Right, 78%. What's the next most abundant gas?
oxygen.
Chemical symbol?
O2.
How much?
Isn't that like 21% or something?
21%, right? And then third,
Argon.
argon. How much?
1%.
And then what's last?
Carbon dioxide.
How much?
I have 0.038% here.
And
Increasing.
increasing and rising. Remember this? This is all unit one. I hope it's in your brain. Okay, so the point is, now we're talking about water vapor. So do you understand that we're going to put some water vapor in that box? And I don't know, it's going to be more than CO2, right? It's going to be some amount. And if you look, I don't know if the book says this, it's usually between 1% and 4%. So I have to take out the molecules and put in some vapor instead. But do you agree that if air pressure is the weight of the air above you, and 78% of the air above you is nitrogen, The nitrogen exerts about 78% of the pressure because it's flying around nitrogen molecules. So water vapor contributes to some amount of the pressure. Well, that's E. That's vapor pressure. It's part of the whole that's a result from vapor because some of the vapor molecules are moving heat in the Walton box. But what is E sub S? What is E sub S?
The amount of pressure at the saturation point when it's saturated.
Okay, I can accept that. So would you agree then that I've got some amount and I have some amount that I could have if it were saturated? Isn't that equal to the relative humidity? Or at least I said about equal to? Do you see that's just like this? Isn't this mass and that's pressure? And this is capacity and this is capacity? So what do you think E is a measure of? What is E a measure of?
Yeah.
Vapor pressure.
Yes, but what is it a measure of? Just kind of what is it? So Isaac, if I were to ask you this on a test and I said, what's E? And you said vapor pressure and I marked you wrong, would you be pissed? You're like, vapor pressure, and I'd be like, yes. But what I'm asking for you is what exactly, I mean, what is it really? Basically, what is E?
It's some of the
I tell you what, what's W?
oh man.
What's W?
Mixing ratio.
What is it though?
Amount of water vapor in the air.
Right? Isn't that what you said? It's the amount of, it's how much there is. What's W sub S?
The amount of water vapor that, no.
Yes.
The saturation mixing ratio.
Well, yeah, but the amount of water vapor
that can be in the air.
Right. So the relative humidity is how much do you have divided by how much could you have, right? So what is E basically? Isn't it still the amount of water vapor that you have divided by how much you could have? Expressed in millibars though, as opposed to grams, which is weight, right? Mass is grams, millibars is pressure. But didn't I say that air pressure is the weight of the air above you? So E is just the weight of the vapor above you. And there's a limit to how much could be there before I got back into a dynamic equilibrium with whatever water's there. Does that make sense to you?
Yeah.
Yeah, I'm going to ask you something because I have a meeting with my boss in a couple of days, and I want to ask you something. How much water vapor is in this parcel?
W.
Right? How much could be there?
W sub S.
Now, answer not using W. How much water vapor is in the air?
There's some amount of water vapor.
Well, other than using W, what could you say? What could you use?
E.
E.
Could say E, right? There's some amount that's causing some of the pressure. And for the most part, it's the same thing. Okay, now that's all I'm talking about. Now you said the Bergeron process, Zach. We're trying to get to where? Where were we in this thing? We said the saturation vapor pressure of ice is less than that with water, liquid water. So what has to be present in the cloud at the same time for this to matter?
Would ice have to be in there?
And
ice and liquid water.
This is the key to the Bergeron process. I need ice and liquid water at the same time. So do you agree that in this scenario, what's in the air? How much vapor is in the air around these guys?
E.
E. What's the relative humidity do with this guy, this ice crystal, versus this guy?
Exerts a force on them, and they collide into them.
I'm asking about relative humidity. Like, do you see what I'm asking you in this thing? What is the ice crystal relative humidity? What's the liquid water droplets relative humidity? But what's different is this, isn't it? Isn't that what it says? What's E? Is E different? What do you think?
Aaron says no.
E is the same, right? E is what is. How much is there? E. It's how much there is. But do you understand that the capacity is something different? It says, well, when will I get a dynamic equilibrium? When will that happen? And I can now think about vapor turning to liquid or liquid turning to vapor. What do you call vapor turning to liquid? What do you call vapor turning to liquid?
Oh, condensation.
What do you call liquid turning to vapor?
Evaporation.
What do you call vapor turning to ice? Or ice turning to vapor?
Would that be sublimination and deposition?
Sublimation. Which one of these is sublimation? Ice to vapor. Deposition is vapor to ice directly. Have you ever put a snowball in the refrigerator or freezer? Did you ever do that when you were a kid? Zach, did you? You look like the kind of kid who
I've
would.
put hailstones in the fridge or freezer
How long did you keep it in there, Sam?
until I cut it in half,
Oh,
maybe about a day or two.
did you ever keep it in there for long periods of time? What happens to it?
Starts getting smaller.
Starts getting smaller. Doesn't it go away? Does it ever melt? No, it just sublimates. You've seen it this year. Look at all the snow that would disappear around trees, even though it never got above freezing. You never saw a puddle of water. It just went from ice to vapor. That's sublimation. The opposite is deposition. And the rate or the ability of this thing to happen and where it becomes saturated is different than the condensation and evaporation. And as a result, the denominator in both of these is different. Which is bigger? Isn't that what it says in the notes? Therefore, what is the relative humidity relative to the snowflake compared to the relative humidity relative to the water droplet? Talk to each other about this. talk to each other about this out loud. That would not be out loud. That's being quiet.
So, are we just continuing like with the Bergeron process, or?
Yeah, well, I'm saying this, right? I mean, whoops, what the heck? I'm still sharing my screen, right?
Oh yeah.
Where was I? Just happened. Where's my notes? Did I have them here? Did I close something?
I think they're on Word.
Oh, here it is. Yeah, sorry. So what do you say? Do you know what I'm talking about? Yes or no?
I found something in the book that looks like it might help. So like it says that the water vapor surrounding the droplet and the ice crystal cannot be in equilibrium both at the same time. So that shows that they are not the same. So that's one, I guess, possible answer. So that's
So if they're not the same, Lena, they're what?
They're different.
Which one's bigger?
Aaron says liquid, the denominator of the liquid.
The denominator of the liquid. So which one has a higher relative humidity?
The ice.
The ice does, right? Because if the denominator is bigger, A equals B over C, the bigger the denominator, the smaller the relative humidity, right? They're inversely proportional. A equals B over C. So when this first happens, what was the relative humidity with the water droplet? Because it's in a cloud. It was 100%. But what happens to the relative humidity with respect to the ice crystal?
It's larger than.
It's larger. So what do we say that it is? What do we say the air around the ice crystal is?
It's super saturated.
It's super saturated. So do we want that to happen? No, supersaturation says some of the vapor's got to come out. So how does it come out? Deposition. You take vapor out of the air through deposition. So what happens to this is it starts to grow. And now what do? I take vapor out of the air until when? Until the relative humidity becomes saturated, since we're back in dynamic equilibrium. But when I take vapor out of the air, what happens to this equation?
It becomes smaller.
Right? The relative humidity becomes smaller. And what was it?
It was at 100%.
It was at 100%. So now it's less than 100%. So what is this droplet going to do?
Just go away.
It's going to start to evaporate. And evaporation starts putting more vapor into the air, which ends up on the crystal. The net result is that the crystal grows by what process? What's the name of the process that the crystal is growing by?
Deposition.
You agree that this guy, look at the TV or your monitor. That's getting smaller. This is getting larger. Ice crystal grows by deposition at the expense of the cloud droplet, which is evaporating, right? This is a very efficient process. It happens really quickly. Whereas collision and coalescence is a very inefficient process when things are small. Now, take a look at this on this sheet. I have a chart at negative, hold on a second. At negative 20, negative 10 degrees Celsius, the ice crystal has a relative humidity of 110%. The liquid water is at 100%. At negative 20, look at the relative humidity. That's really high supersaturation. That means the vapor comes out very quickly, even though the water droplet is. So in other words, what has to happen for the Bergeron process to begin? You have to have ice and water at the same time. Well, why do we do that? Why does that happen? Between these two guys, who has a higher entropy?
The water droplet.
The water droplet, because you agree the water molecules can be all over the place. This crystal is extremely low entropy because it's ordered, it's structured. What is the structure of ice? It's a crystal. What is an ice crystal? How many sides is an ice crystal? Do you know?
6.
What's that called? What's the shape name?
Hexagon.
What'd you say, Zach?
Hexagon.
Yep. It's hexagonal. Okay, that's really ordered. You have to tell all the water to line up just a certain way. Now, here's the thing about it. In order for this to happen, to get that order, it takes a lot of forcing. I want you to think about if you were a teacher running a kindergarten class, and you said to the students, "Hey, everybody, line up." How do kids do when a teacher says line up? What do most kindergarten kids do when you say line up? You were all children at some point.
Not line up, run around.
Yeah, you were just kind of like, and it's not that you're trying to be mean, you just don't know what to do. You're walking around like sheep. So what does a teacher do to line you guys up? You know what kindergarten kids look like. Imagine you had a bunch of kindergarten. How would you line them up? Wouldn't you grab a couple of them and go, stand here, and move them into a line? And once you start the line, what does everybody else do? Now they figure it out. Right? Once you start the line, everybody kind of gets in the line. So teachers are always like grabbing kids. You stand here, just stand there. And then everybody lines up. And that's even true as an adult. If I went into a room with a bunch of adults and said, line up, you'd all be walking around like lost sheep. Once you start the line, everybody kind of follows. Right? You ever been to some places where there's a line waiting to buy stuff? And you're always like, are you in line? Are you in line? And then once you see that there's a line, everybody knows where to go. Right? Except for the occasional clueless person who cuts in front. You're like, hey, dude, there's a line. Right? And you tell them to get in the back of the line. This is how life goes. So what we need to do is give the ice crystals something to line up on. What is that called?
Aerosol.
It is an aerosol, but it's a special aerosol. It's called a freezing.
Cloud condensation nuclei.
Not nucleus. Oops. Nucleus freezing or an ice. You're going to read something about it. It's called an ice forming nucleus. Now, this is not a CCN, and why is that? What's special about a freezing nucleus? Really, what we'd say it's sparse. What's special about it? It's similar in structure to ice. So if there's something, and there's, there might be clays or there's certain kinds of things in the atmosphere, and you're going to read about it, looks similar in structure to ice. And that, once that happens, then the water will start to freeze onto it. But there's something else important about this. When does ice freeze? When does ice freeze? What temperature? Do me a favor, do a web search. At what temperature does ice freeze? And tell me what you find out. So do a little search and see if you can find that out.
Makes a difference.
Okay, so a pure water droplet freezes at -40. Once you get to -40, that cloud droplet, no matter how small it is, will freeze. It'll turn to ice all by itself. Right? But can you make it freeze? So why do we say that water is at 0 degrees Celsius? Why is it freezing?
That's like ground temperature.
But why that? Now look, imagine that you had your windshield on a really cold night. Do you agree that you normally will spray water on it? Maybe with like windshield wiper fluid. And maybe you don't have that good stuff and it freezes too quickly. Describe how it freezes. Does it freeze all of a sudden at once everywhere? How does ice freeze on your windshield? Or maybe on your window or whatever?
Slow transformation.
Right? Doesn't it start someplace and grow? Now here's the question, Zach. What is temperature defined as?
Isn't temperature the amount of radiation we take in compared to how much we radiate ourselves?
Well, that's what changes the temperature. But what is temperature? Definition of temperature.
Oh, isn't it like the kinetic heat or the kinetic energy of molecules moving around?
You're missing a word. What's the word, Aaron? I almost called you Kevin. What's the word, Aaron?
He says average kinetic energy.
It's the average kinetic energy. So if I have a puddle, do you agree that I have millions and millions of molecules? And would you agree that the average temperature is 0 degrees Celsius? But really, there's places in it that are probably really cold. And what do they start forming? An ice crystal. But once that forms the ice crystal, all the other molecules can line up. So when you see ice forming, ice starts to spread out. It forms this crystalline structure, and you see it form someplace, and then it builds this sheet of ice. In fact, if you look at a puddle in the wintertime, it's a very thin sheet of ice. Then the temperature below gets a little bit colder, and you get these layers of ice. So if you ever broken a puddle, you actually see sheeting going on. That's because the crystals are lining up. When you have a puddle of water, it's a lot easier to do this. However, when you have a really small droplet, remember we talked about, you could talk about surface tension, but if you think about it in terms of entropy, to go to a crystal, which is a low entropy, highly ordered, it takes more effort to do that. So it doesn't happen till about -40 if it's pure water. But is it pure water? No. You come in contact with something that already has a crystal structure. In the module, we're going to be calling it a crystalline lattice, L-I-T-T-I-C-E. Do you know what a lattice is? Do a web search on lattice or look at images for lattice. What does that word mean? What kind of stuff do you see on there?
It's like a diamond formation.
Okay, so some of them are diamond, but what are you using it for? Where do we use lattices?
Like fences.
Like fences, right? Gardens, fences, and then the vines grow up the lattice, and it's a structure, right? It's a lattice. It's a structure that gives something to support. So I have this structural support, and now the water vapor molecules go around and start forming a crystal. The thing is, those particulates are not very common in the atmosphere. So when I did this, right, I'm sharing my screen, I think, yeah. Is it recording? Does it say that it's recording?
Yeah.
Okay, good. What happens is they have to be similar in structure, and there's not that many. So in the cloud, there's going to be 10, you're going to get anywhere from 10 to 80, 90% ice, and the rest is liquid water. But the water is still water, even though it's below freezing. So what do we call it? What do we call water that's below freezing? It's super cool. Because it's super cool and these things are rare, there's a time where you're going to have both ice and liquid, super cool water at the same time. And that's what allows the Bergeron process to take over. But the last thing about this is it doesn't just happen at 0. When do these things start to turn into ice? They become activated at, let's just say around -10 degrees Celsius. So if I have a cloud, let's say I got a big cumulonimbus cloud, and in the cloud I have an isotherm that's 0 degrees Celsius. And over here, there's an isotherm that's -10 degrees Celsius. And over here, there's an isotherm that's -40 degrees Celsius. Why do the isotherms bend up?
Latent heat.
Yeah, and what does this tell me then? What's the temperature? What's the temperature right here?
Like -2 degrees Celsius.
Okay, -2, something like that. What's the temperature here?
Still -2.
Do you agree that it's warmer than outside the cloud? That's why it's buoyant. So what is the cloud made out of when the temperatures are warmer than freezing? It's all liquid water droplets. Do you agree? It's all cloud droplets. What is this? So this region here, let's call it region A, is all liquid. What's region B? What's the cloud made out of at region B?
Liquid.
Droplets and ice.
No, because remember, when does the ice start to form? At -10. So this whole area is going to be super cool water droplets. We'll talk about that in a second. What's going to be here in this region C between -10, -40? What's the cloud going to be made of there?
Ice and liquid water.
Some ice and some, don't just say liquid water though. I'm just going to clarify. What would you call that water?
Water droplets.
Well, it's special. What about them? They're water droplets, yes, but they're,
Super cool.
aren't they super cool water droplets? So you have ice and super cool water. Then what is colder than -40 up at the top? What is this?
It's all ice.
It's all ice. So what kind of a cloud would that be? What kind of a cloud is all ice? Lena, what'd you say?
Oh, you said all ice? That's a cirrus.
Cirrus, right? So in a thunderstorm, that's the anvil, is all ice. Cirrus cloud, that's region D. So which letter, A, B, C, or D, is going to be where the Bergeron process grows precipitation? On the count of 3, tell me the answer. 1, 2, 3.
C.
C.
The Bergeron process requires letter C, right? It requires liquid and ice. Now, what's special about region B? It's really bad for airplanes. An airplane.
Isn't B the dendritic growth zone?
No. Hold that thought, Sam, because we're going to talk about that in a second. This is where you get a condition known as icing. So a plane flies through all supercooled water. Do you agree that water will collect on the plane? But the more water that the plane runs into, what will happen to the droplets?
It's going to start forming ice.
They're going to get bigger, aren't they? And the bigger they are, the easier it is for them to form ice. So you start coating the wing with ice. That's what icing is. Then the plane can't fly. That's bad. So airplanes avoid region B because that's where icing takes place. This is where you get the Bergeron process because you need liquid and ice. And in the Bergeron process, the ice grows at the expense of supercooled water. Now, what Sam was saying, there are different types, types of crystals. That's called their habit. Habit says, what does the crystal look like? Okay, so I'm going to share this with you for a second. I'm going to go someplace. And I want you to do a Google search on this. Ice crystal habit. And if you go here to, oh, I don't want videos. Let's go to images. Here's some examples. This is actually a pretty good drawing right here. Now let's get a bigger one. That's good. Okay. So when the temperatures are at 0 to -10, hold on, let's do this. Can I erase this for now?
Uh,
When the
You go
temperature
back.
is 0 to -10, I
Can you go
get,
back? I was going to take a screenshot of that.
you should give me a second. Well, you can do a screenshot. You can,
All right, thank you.
okay, but that's okay. Okay, so over here, you start getting cold, you get these things called plates. When you get up here, you get needles or solid columns. But over here, you get these other things, and then you get these guys. This is called a dendrite. A dendrite is like you would draw a snowflake. Like if you're cutting a snowflake with paper, 6-sided, pretty crystal structure. That's called a dendrite. Okay? Dendrites grow and cause a lot of snow. If it stays as dendrites, it's going to be a lot of snow. So we have what's known as the DGZ, which stands for the dendritic growth zone, DGZ. And that is, again, we could argue about this. I'm just going to say about -12 to -18 degrees C. And at this temperature, so if I go over here to this temperature, hold on, let's do it this way. At -18 to -12, do you see that is where the greatest difference in the relative humidities is? You're going to get big differences in relative humidity in this area, and that's where you get dendrites to form. And that's what you want for heavy snow. So you want the air, listen to what I'm saying, you want the air to be saturated throughout a large layer in the DGZ. And when that happens, you're going to get heavy snowfall. That's called the DGZ. Now, let me show you something. Any questions on that so far? Let's do this. Let me go show you something that's really interesting that's going to happen this week. Look what's happening in Colorado this weekend.
Wow.
There is some heavy snow going on. By the way, if you want to say how much snow do you expect, look at the values in there. That's a big snowstorm. So let's go to this. Now I'm going to show you a sounding in this area. Oh, no, hold on a second. I want it to be winter weather soundings. And I'm going to take a sounding over here in Northeast Colorado. The red is the temperature. The green is the dew point. Would you agree that the air is saturated, or at least really close to being saturated, from pretty much the ground all the way to 250 millibars? That means we have this really, really thick cloud. If you look over here, that yellow line, that's the DGZ. It's in here. Now, the only thing that's different about this from what you would have drawn on your graphs is this is the 10-degree line. This is the -20 line. They're skewed. They bend over a little bit. So that's where it's between -12 and -18. So it's saturated throughout the entire air, like almost the entire troposphere is saturated. This is where you're going to expect a lot of ice crystals and liquid water, and that's where the dendrites are going to grow big. Now,
Oh, wait.
go ahead, Sam.
I know this is kind of technical, but isn't that sounding contaminated
Why?
because of the omega?
Well, you've got rising air in here. That's what this is. I mean, it's just set. You have vertical motion throughout the entire atmosphere. So this is the DGZ. Okay. So when I get colder up here, what's going to happen? Here's -40. What's all of this going to be? Ice. So here's the thing. When the ice crystals start to fall, do you agree that those ice crystals, what's more similar in structure to ice than ice itself? So these little crystals are going to fall and they're going to actually do cloud seeding, and all the liquid that comes in contact with it is going to, or the vapor is going to start to sublimate. I'm sorry, deposit. You're going to get, dendrites are going to grow a lot through this whole layer. And then as it falls, does the temperature ever go above freezing? And the answer is no, it's always, so will this snowflake ever melt? So the snow will fall and it will fall to the ground as snow. And it's going to be a pretty significant snow. Now, there is something, what if a snowflake fell and it came in contact with another snowflake? Near temperatures near freezing, they get a little wet and they form together. So two snowflakes coming together are called aggregation. So write that down in your notes. Aggregation are two snowflakes sticking together to form a bigger snowflakes. So have you ever seen it when it's like those really huge snowflakes falling? Usually it's above freezing, they're wet, they stick together just like you pack snow. Those are called aggregates. You get those really big snowflakes. We call them, oh, look at those aggregates. Okay. Now, some of the times, super cool, you have a big snowflake here, right? You got a big dendrite. And what happens if the dendrite gets together with the super cooled water? That water will freeze when it comes in contact with the snowflake. That's called accretion. It accretes, or sometimes we call that rime ice. And so instead of having a snowflake like we'd see, we start to get water that forms on it. It becomes this kind of this icy little thing, and that's sometimes called grapple. That's called grapple. So let me show you something here just for a sec. If I said, look for grapple, and I go to images, you've seen these things. What does that look like to you? What thing that you might eat in the summer does this look like?
My sister literally said it was raining Dippin' Dots, so I'm.
That's what it's called, Dippin' Dots.
Yep, Dippin' Dots.
Okay, so when you see it falling and it looks like Dippin' Dots, And you all know what Dippin' Dots is, right? There's nobody. I love Dippin'. Does anybody like Dippin' Dots? I think they're awesome.
Oh, I love Dippin' Dots.
Just love them. So those are called snow pellets. They bounce, but they're squishy. They're like little styrofoam. If you ever just grabbed it, you kind of squish it. Do not confuse snow pellets. So those are snow pellets, which is grapple, with ice pellets. And what do we call ice pellets? What's the common name for ice pellets?
Sleet.
That's sleet.
I was once told that you start seeing bigger snow pellets that may indicate the possibility of thunder snow. Is
Well,
that
yeah.
true?
If you see grapple, Sam, the rest of you don't need to know this, but if you start seeing grapple, you probably have some convection within it, and it may be enough convection to generate lightning. But yeah, grapple usually has a little bit of an upward convective motion to it.
Similar to hail, yeah.
Yeah. So the difference is this stays, right? Grapple forms because a snowflake gets covered in supercooled water. Grapple. An ice pellet is when the snowflake falls, it goes to the zero, it goes above freezing, and then what does the snowflake do? It melts and becomes a raindrop. If the raindrop falls and it goes below freezing, it freezes as sleet. It's a frozen raindrop. So grapple at the core is a snowflake. Ice pellets are sleet. At the core is a frozen raindrop, a raindrop that turns into a little chunk of ice. Right, that's what we said what that was. If it falls to the ground and the ground is below freezing, then it falls as freezing rain. Right? That's what freezing rain is. It falls as water, freezes on contact. So grapple is snow that gets covered in supercooled water and falls as little snowballs, Dippin' Dots. Sleet melts, refreezes. Freezing rain melts, refreezes when it comes on contact with the ground. Most of the time in the summer, it will always stay above it and then you get rain. Now imagine that we had a raindrop coming in contact with another raindrop. What's that called?
Coalescence.
That's collision and coalescence, right? So raindrops collide and coalesce. Snowflakes collide and aggregate. A snowflake touching supercooled water is accretion. So let me do this for a second. Here's the difference between sleet and grapple. Sleet's usually pretty clear because it's frozen raindrops. This is snowballs. Here's a snowflake covered in grapple. It's rimed. So if I were to do grapple and I would go rime ice, this is cool. See this snowflake? It's covered in rime ice. This one, look at that. This one's cool. That's almost a piece, that's almost like a solid grapple. But it still has its shape. So when you look at all these things, this is what ice crystals look like. Okay, and that's all the habits of snowflakes. So let's do a couple. Ice crystals, snowflakes. Let's look at some pictures of snowflakes. And they're beautiful. These are dendrites. Isn't that gorgeous? Modeling snowflakes. I mean, they're so beautiful. But do you agree that these, like I look at this and I think, God, those things are low entropy. No, I'm not that big of a geek. Let's do this. Let's look at sectored plates. Here, those are sectored plates. Come on, these are cool, aren't they? You like this? Do you like looking at snowflakes? Anyway, so that's the sounding coming in for Colorado, and it's going to be snow. And they're going to get a hell of a lot of snow.
I have a question.
Okay.
Before the two biggest snows we had this past winter, I noticed that there was the grapple right before, like when it was transitioning to heavy snow, but before the actual big snow hit, it did grapple before both of those. Is that like normal? Is that something to do with the process?
Yeah, that would be definitely the process. It depends on how cold the layer of air is. Right?
Okay.
So if you get a better DGZ, you get more ice crystals. If you don't get a DGZ, like you could, what if you had temperatures below freezing, but not below -10? What would almost the entire cloud be made out of? Colder than freezing, but above -10. What would the cloud be made out of?
Super cooled water.
It'd be all super cooled water. Would you get would you get the Bergeron process generating precipitation? So you'd get drizzle. But because it would be liquid drizzle, but then when it comes in contact with something, it should freeze because it's below zero. So we call that freezing drizzle. Right? Freezing drizzle doesn't cause like power lines coming down, but it does cause icing really bad. One of the worst COD mornings, we had nothing but freezing drizzle. It was like, it just got weird out. I've never seen that many accidents in my life. You go to like Google Maps or something and it's just accidents all over the place. And it wasn't even accumulating, it was just so bad. Nobody can drive on freezing drizzle. So here's our forecast, by the way, if you want to see this. This is kind of a bummer, if you ask me. So I'm going to show you something. There's rain coming in, maybe some thunderstorms this week, yay. But then look at this. This is Sunday night into Monday. It's going to be snowing. You want to see how much snow they're looking at? And we've got areas of 4 to 6 inches of snow coming in. Maybe. I'm not saying this is still a long way away, but it's possible. So, Lena, you were outside. It's nice.
Yeah, we still have a chance of thunderstorms today and tomorrow. I'm happy.
Okay, well here, what's the measure of instability called, guys? CAPE. So let's take a look at CAPE for the next couple of days. There's some CAPE coming in. Any area of color is CAPE. So we do have an area coming in Wednesday night into Thursday with the potential for CAPE in our region. Sam's up there in Madison. So he's looking at 6Z, so overnight, Thursday night into Friday, and we have the chance for thunderstorms. So let's do this. Let's take a look at a model product, and we'll look at where it's going to rain. And we at least have something. So let's take a look at a sounding here. Oops. Let's look at a sounding. It's like the things that you draw. And how much CAPE is there? Well, not that much, but let's say 228. That's enough to get a thunderstorm. So we have the possibility, there's a little bit of PBE in this area, not much. But we do, here's our forecast. So we'll start with DuPage County.
I wouldn't expect any severe weather.
Slight chance of showers in the evening, then showers and a slight chance of thunderstorms after midnight. Slight chance of thunderstorms in the morning. Woohoo! That's exciting. Sam, where are you? You're up here in Madison?
Yep, it's the
Which county?
Dane, which is the middle.
So here we go, Dane. Light rain and showers and slight chance of thunderstorms in the morning. Chance of thunderstorms at around midnight. So you have a couple times of thunderstorms. By the way, have you noticed how lame the severe weather is this week? Sam? Sam?
Yeah, yeah.
And who told you? I told you it was not going to be good.
I literally just said it's not. I mean, I'm not expecting any here.
Right, but I told you that before, and you were like, "Oh, maybe severe weather." I'm like, "No." I mean, there's a possibility of maybe some hail tomorrow in this area of Kansas, but it's just a really horrible setup. Maybe this weekend down here in the south, these are severe weather. But does that make sense to you guys? Do you see how this all works? All because of the Bergeron process. So I have well, you know what? I'm going to review this, but what I'm going to do is this. Because you guys kind of took a little bit more time from me, I'm going to assign something for you right now. And I'll give you the information for it, okay? So this is, I need to redo this. Maybe I'll do this some point. I'll copy this. I'm going to send this. Stop share. I'm going to chat you on this one. Here's the link. Oh, that's the same. I wanted to send to everybody. And that's a lecture. Oh, wait. It's at climate. So if you want to know how to find it, it's climate.cod.edu/classes. But instead of 1110, like you find yours, go to 1119.
You put that up?
Here, if you guys want to do, Kevin, what do you want? Here.
I really can see it.
Let me show you. Oh, hold on. I sent it on the chat screen. But here, I'll do it this way. So if you go to climate.cod.edu/classes, which is where we find our lectures, you're going to go to 1119.
Okay.
And there's a Cervatka lectures, and then there's topics and precipitation type forecasting. And it's going to go through a module, and we're going to, and it'll give you some cool little videos, but watch that lecture. It's 38 minutes long, so I'm going to let you go early. Okay? So that you can do that. And then if you have any questions on it, so take notes on this module. I want to see what you can do, but that'll give you some more stuff where there's a little bit more information on it, and you can read through that. But that's the Bergeron process. That's how we get precipitation. So remember, we start thunderstorms, we start rainfall, snowstorms with the Bergeron process. Collision and coalescence helps later on. But it's the initiation is the Bergeron process. So Kevin, is that good? Are you all right with that?
Yeah, I think so.
Okay. If you have a problem, just let me know.
All right.
Okay, is that good for everybody? So I'll let you do that now. You might as well do it now. It's just a lecture, but take some notes on it. It's a little bit more passive. You don't have to worry about it. It'll be a nice refresher and a review of what we just did. Good enough? Okay, guys. So watch that now or watch that later. Maybe you should go outside and get some warmth, but watch it before Thursday's class. We're almost done. I'll tell you what we're going to do, and we'll talk about the test on Thursday, okay? Questions, comments? Okay.
Right.
Have a good week then. We'll see you on
Have a
Thursday.
good day.
Thank you.
Have a good day.
Bye.